All right. Now let's continue. Last time we basically finished when we have a system of two-dimensional differential equation with linear system with constant coefficients. What we did is actually we take out A, and we say, well, we study the eigenvalue and eigenvector. And then it gives us nice solutions looking like this, which is a straight line solution. Lambda and V. Okay. Then we were able to handle, how to find the general solutions for the first case, when we have two distinct real lambda 1, lambda 2. Turns out they are straight line solutions, and once we know the straight line solutions, we either have this case or that case. We can determine source, sink automatically. And if we know both are sink, the whole thing is going to be a sink. Both are source, the whole thing will be a source. If one is a sink, one is a source, we are going to have a very interesting case, which is we have a saddle. Of course, we have several cases. Number one, what if we have repeated real eigenvalues, which means we only have one eigenvalue instead of two? What if we have zero eigenvalues? And what if we have complex? For the next few sections, we are going to handle them one by one. So the first thing we will be handling for today is going to be what will happen if we have two complex eigenvalues. Okay, so that will be the focus for today. So number one, complex eigenvalue and eigenvectors. The first thing you want to keep in mind is, especially for the case we have, why do we have eigenvalues which are complex? Let's take an easy system and do the same operation we have done so many times before, and try to figure out what is lambda, what is v. Okay, and then what we can do is we can say, well, determinant a minus lambda I determinant. So we have lambda plus 2, 3, negative 3, lambda plus 2. This gives you lambda squared plus 4 lambda plus 4 plus a 9 equals 0. This gives you lambda squared plus 4 lambda plus 13. If we are able to factor everything out, we got two distinct real eigenvalues. We repeat what we had in the previous section. For now, you can see it's not going to be working. The only thing we have is we have to go with the quadratic formula. And suddenly we realize, okay, there's no way I can get two real solutions because of this. Okay. Instead, I will have I, which is the square root of negative 1, which gives me two eigenvalues again. Simply because when we solve quadratic equations, we have a case that we can have two complex values. So the first comment, or let's say remark, lambda 1, lambda 2 appears in pairs. You will never have one complex value. You either have two, or later maybe you either have 4, but you will never have an odd number, because automatically if a plus bi is a solution, then a minus bi is also a solution. They are conjugate to each other, so you do have two complex eigenvalues, and they actually have certain kind of symmetric relationships. Okay, so that's the first thing we have. Okay, so it's possible that we have eigenvalues which are complex. Now, how does that affect our solution? Well, let's think about it. We started from here. Okay, we say, well, my solution looks like this. Okay, so as long as I have two solutions and they are linearly independent at time 0, all possible linear combinations is going to be this one. And this is guaranteed by the linear property of the original DVQ. So even for complex eigenvalues, it still have linear property. Therefore, this idea will still work. Now after that, what did we do? We said this one is going to be e lambda 1 v1 plus c2 e lambda 2 t v2. And we claim these two are linearly independent and they are both solutions, and they are both straight line solutions. Now you can see this time it's gonna fail because this only works for two real distinct in order to get two straight line solutions. So this step still work, but this time fail. Okay, for complex. Well, then what can we do? How can we actually end up solving this? How do we do that? Well, even if this one fail, we can still follow the same spirit. That is, we do want something like this, where lambda is the eigenvalue, and v is technically the eigenvector. Do I still have eigenvalue? Yes, it's complex. Do I still have eigenvector? Yes, and when I solve it, it's going to be complex too. Okay, so I may still have this kind of format. My trouble is maybe this kind of format won't work anymore as a solution. So does it work? Let's try it. Let's try it with this example here. So we already have AV equals lambda V, where if we let V equals AB, just as before, and pretending we didn't see the complex, we just follow the logic, follow the calculation. So what do we have is -2, -3, 3, -2, V, which is AB, equals, we have the first one, which is 2 plus 3i AB. We don't like it, but we keep it. Then what are we going to get? We are going to get this one, minus 3b, equals 2a plus 3ai. Meanwhile, 3a minus 2b equals 2 plus 3ib. Note, this time a and b can be complex, because you can have complex numbers, right? Before they're all real. Then if you solve the first one, we have something is wrong. This is negative. What did I have at the beginning? Negative. Okay. -2a plus 3b. No. -2b plus 3bi. Okay, so now if you do it on both sides, what we are going to get is on the top we have -3b equals 3ai. This implies b equals -ai. Okay, and for number 2, you are going to have 3a equals 3bi minus. Yes, this implies b equals, somehow something is wrong. Did I copy the wrong thing? 3 -2, no problem. -2 plus 3i plus 3ai -b. Okay, then this equals that. Okay, good. And we have 3a equals 3bi. Oh yes, so b equals a divided by, which is also -ai. All right, so with that in mind, the vector will look like a, b, but then it will look like a, -ai, which give you a times 1 -i. So this is going to be your eigenvector. Okay, with that thing in mind, now this is what we have. We have an eigenvalue. We also have an eigenvector. Okay, so our solution can still have something look like this, which is going to be e to the -2 plus 3i times this. This is going to be our solution, which we got from here. Okay. Not to mention we still have another pair, which is e to the lambda 2t, v2 equals e to the -2 minus 3i, okay, times something. And finally, our solution is going to look like this. if we just want to, recklessly follow what we had before, then we are going to write this down. Let's save that thing for a while. For now, okay? Later we can find this vector if we want, following the same procedure. But this is basically will be what we are going to do. We're going to do the same thing for lambda 2. We found another v, which involves complex number. Now we basically put these two together into this. This is not going to work. Or at least not clean. Okay? So we do have two methods we want to think about. The first one is what we mean by this. Here I have a t here. I forgot. Okay, lambda t, right? Okay, and second, how to handle complex. That's the two questions we have. Now we are going to name this question 1, Q1. We're going to name this question 2, and we will try to answer them. Okay, and for now, we will focus on only the first solution given by this. Later, we will try to add some patch to actually tell you what we are going to do to this side. Okay, that's for later. So for now, let's just focus on the first one. Okay, that is, how do I interpret this? Well, the first part is how do we handle this Q1? And that is by Euler's formula, which we did before. We briefly mentioned. You can prove it by using Taylor expansion or other methods, but basically that's a fact we know. That is EI theta equals cosine theta plus I sine theta. Therefore, when you see a complex number represented into the power of E, what you can do is, number 1, you have this, and then you can split it into the real part and the imaginary part. Then, by the property of E, you can do this one times e to the 3it, or let's change it to be I 3t, just rewrite everything. Then you can realize for the real part, there's no problem, that's just a number. For the complex part, with only a I, no real part, we apply this formula. That is exactly e to the I theta, with our theta equals 3t. Therefore, the whole exponential here involving I can be rewritten as cosine theta, where theta is 3t, plus a sine, I sine 3t. So this equals that. Okay. Or more precisely, we can write down the general format, that is e to the a plus b, I, should equals e to the a, there's a t, e to the at times cosine bt plus I sine bt. That's how we interpret the exponential of e with a complex number as the exponent. So we are here. So first job done. Now question 2, how do we understand this times a complex eigenvector? Okay, how do we understand that? Well, for this one, what we can do is, number 1, the first part is done. Okay. Second, now let's multiply everything together and distribute everything. Okay. The bottom is going to be this. Okay. Note I and I give you -1, so I switched to put the real part first. You can do it, you can pause the video and try to make sure that you are getting the same calculation as I do. So basically what I did is I used this one to multiply the -I on the bottom, and when I finish, I arrange them such that all the real part goes together and all the imaginary part goes together. Of course, I'm missing something here. if I want to expand it, it's going to be this. Okay. So now what we do? We can actually write them out into two parts. That is the real part, which we got from a complex times a complex. Of course, you have a final complex vector. And then you can actually differentiate, separate the real part and the imaginary part. Okay, that's what we got. If we put a negative here, that would be perfect. Okay, so what do we got? Number one, we take this expression. We change the first one to be involving cosine, sine, and I. That's fine. Second, we multiply a complex number with a complex vector. Of course, we end up with a complex vector with all kinds of I and no I. But then what we can do is we can separate them to be the real part, and the imaginary part, the part with I. Okay. Now, what we want to claim is we can easily prove that this provides one solution to the original diffq, and this provides another solution to the original diffq. Okay, so let me explain. Actually, let me write it down as a theorem. Okay. Complex solutions. Do I want to do it here? Yes. Yes, complex solutions. Okay, here's the theorem. If yt is written as a complex form, like the one we just did, equals y real plus I times imaginary. Okay. Then both this and that are solutions to okay, this we need to write down for the diffq. So assuming you already have a y and this y satisfies the diffq. For y satisfying, we better just be careful here. Hopefully I don't have to rewrite anything. Okay. For y satisfying, y prime equals ay. Okay, so this is what we are trying to do. We solve everything we did before, so of course we know the y we just wrote down in terms of like a complex vector will satisfy the original differential equation. That thing is going to have two parts, the real part and the imaginary part. Now what I'm saying is, even though I write down one solution, but actually I already have two solutions because the real one gave me a solution, the imaginary one also gave me a solution. Okay, so for that we need this theorem. Let's do a simple proof, very easy. Okay, assuming you already know y satisfies this. That simply means this one satisfies this because your y is in a complex form. A real y plus I imaginary y. Now on the left you have this. Okay, plus I imaginary y prime equals a real y plus I imaginary y. Now on the left you have a complex number, on the right you have a complex number, a complex vector. Therefore, the real part should equals to the real part, and the imaginary part should equal to the imaginary part. So we put the one with i's together. They have to be the same in order for this equation holds. We do have real y prime equals a real y prime. That's another way to say real y satisfies the differential equation. Okay. Similarly, we have so if you can write down the solution into a complex format, even though you only have one solution, which is a complex vector, a solution, but actually you already have two, because the real one will satisfy the original differential equation, and the imaginary one will also satisfy the original equation. Okay, so that's what we have. Now, can we find the solution now? Well, what do you need? You need the final solution look like this. You need a y1, you need a y2. And once you solve the complex solution, you do have 1 and a 2. You do have two solutions. Then you can just take any possible linear combinations of these two, okay, and to finish the thing. Because that's already enough. You need two of them, and they are linearly independent. Therefore, do it. You will get all the solutions. Okay. Then the solution is given by y equals c1, real part of y, that's one solution, plus c2, imaginary part of y. Okay. Then what do we get? Let's think about it. What we get is, let's recap. Okay. We get this matrix. We solve it. We find lambda 1 equals -2 plus 3i with the eigenvector 1i. Lambda 2 equals -2 minus 3i, negative I. Okay, with some vector we didn't compute. All right, and then we say, well, we take the first one. We do e to the lambda 1 t, v1. That equals e to the -2 plus 3i t 1i. For this part, we use Euler's formula. And after that, we generate cosine sine I. After that, we actually use this one to multiply this one. And eventually, we were able to rewrite it into a format. That is so I was able to separate these two. To be the real and the imaginary. Then, according to the theorem we just said, if you have a complex solution satisfying the original solution, original DFQ, that means this part satisfies it, and this part also satisfies it. If you plug in 0, the first one give you 1, 0. The second one give you 0, -1, and of course they are linearly independent. Therefore, the final solution can be written as C1, okay, plus C2, this. That will be the complete work you need to show to find the general solution of what's going on. All right. So basically, you start with something. You got two complex eigenvalues. You focus on one of the eigenvalues. You get one eigenvector. You do all the computation and assuming your solution still looks like e to the lambda t times v. And then you got all the solutions because you got the real part, you got the imaginary part. You only need 2, and these 2 are sufficient. That's basically the way you solve a complex system, a system with complex eigenvalues. Of course, you don't feel good because you basically didn't finish the other half, right? We didn't do anything with regard to -2 minus 3i. So maybe that's some side topic we want to talk about. What about the other lambda? Seems like you can get all the information from one lambda. But what about the other one? Now what I want to show you is the other one actually gives you the redundant solution, which means if you follow this one, you actually go and find the eigenvalues and eigenvectors for -2 minus 3i. It will give you the same 2 solution here. Therefore, doing one, you will get both because the other one will be the same thing. Okay, and to show that, I will just write down a very simple fact. Okay, so assume lambda 1 equals a plus bi, and the lambda 2 will be a minus bi because they appear in pairs. Then, okay, and v1, the eigenvalue for the first one equals to real v1 plus imaginary v1. Then automatically we know the other one. For this lambda, it's just going to be the same thing with a minus sign. That's what we're trying to show here. Okay. Then, getting one pair of eigenvalue and eigenvectors, the other one will be exactly symmetric, therefore would produce you with the same 2 solutions. So you only have to do it for once, thanks to the symmetry of these 2 solutions. Okay. Proof. Well, if you already know lambda 1 equals a plus bi. All right. And okay, if you already know lambda 1 equals a plus bi, then you already know a v1 equals lambda 1 v1 because it's an eigenvector and eigenvalue. Then what you're trying to say is a real v1 plus I imaginary v1 equals a plus bi real v1 plus I imaginary v1 Now again, on the left you have a real vector plus a complex vector. Okay. On the right, you will also have a complex vector, but now you will need to actually simplify everything by multiplying them out. A real v1 minus, now I and I together, b imaginary v1, that's the real part, plus a I a imaginary v1 plus b real v1. Okay, then what you can write down are the following. The real part equals the real part. The imaginary part equals the imaginary part. A real v1 equals a real v1 minus b imaginary v1 A imaginary v1 equals A imaginary v1 plus B real v1. All right. Finally, you have A real v1 minus I imaginary v1 which is what we're trying to get for the second eigenvector corresponding to A minus BI. Okay. Everything so far we just proved that this one works for A plus BI. Okay. Then this one is going to be the top minus the bottom. Minus B minus I okay, which equals, you can verify by yourself, A minus BI times real v1 minus I imaginal v1. Okay, it's very easy to do. You can just verify by yourself. But then you just proved A acting on this vector equals A minus BI acting on this vector. Therefore, this is an eigenvector for lambda equals A minus BI. Okay, that's the proof. So judging by what we have here, we have lambda 1 equals this in the example. Which equals 1, 0 plus I, 1, negative 1, 0, negative 1. Okay, then we automatically know this one is going to be v2 equals 1, 0 minus I, 0, negative 1, okay, which is going to be 1i. So that's what we got. If we already know everything about the first eigenvalue and eigenvector, we can get everything with regard to the second eigenvalue and eigenvector by flipping the sign involving the I. So plus 3i become minus 3i. Plus I, 0, negative 1 become minus I, 0, negative 1. So you do it for a second time. If you just want to do everything for here, you can try by yourself. You will get exactly the same real and imaginary solution here, except this is going to be a negative sign. But you only care about the real and the imaginary part. You don't care about how they are connected. Therefore, you will still have the same solution. So doing the whole thing for one complex eigenvalue is enough to find both solutions. That's basically what we have. Try some examples later by yourself. Okay, make sure you understand how this process works. So basically everything works as before. Okay, you can still find lambda, you can still find v. Okay, but after that, things works a little bit different is when you plug in this and you try to switch it into real plus I imaginary part, then this give you a solution and this give you a solution, so you don't have to actually do both eigenvalues anymore. Okay, so that's what we got. All right. So now we know how to solve the system. The third thing is we want to talk about how do we determine equilibriums. Moreover, like what is a sink? What is a sink? What is a source? And what is a saddle? Or phase portrait, because we know we don't have straight lines anymore. Well, let's write down the two solutions we have. The first is let me see, y equals cosine 3t sine 3t. And make sure. Yeah. That's c1 plus c2 e to the negative 2t sine t 3t negative e to the negative t cosine 3t. So what do we have here? Let's take the first one as an example. How do you understand this? Well, that's basically x equals this, if you want to draw it in the xy plane, and y equals this. Does it look familiar? Well, technically this is e to the negative 2t cosine 3t sine 3t. Now, what does this part do? We can decompose them into two parts. They are vectors. Let's think in terms of vectors. Number one is pretend. Let's pretend that the cosine, the e to the negative 2t is not there. What does cosine t and sine 3t do? Well, basically what it does is actually it gives you a circle. And moreover, you move along the circle, right? That's basically what you do. Okay, so if that's what you do, what will happen if we add this one? That means as this vector representing the circle keep rotating this way, the vector also becomes shorter and shorter and shorter. Okay, with that in mind, now we can decompose them into two parts. This part gives you a rotation on a circle. You just rotate as a circle. It tells you how fast it rotates. It tells you which direction it rotates. This one tells you how the radius change as you rotate. Okay, so in other words, you are going to have something keep rotating on a circle if the e to the negative 2t is not there. But if the e to the negative 2t is there, then when you are rotating, you also become shorter. And eventually you get closer and closer to 0 no matter how you rotate. You can see this one provide you a spiral. So two distinct real eigenvalues give you two straight lines, and the two complex eigenvalues give you something which is rotating in spiral. Okay. Moreover, if you have the a plus bi, which give you e to the at cosine b t plus sine bt with I. Moreover, we can view this as two parts. The first part will be this. This tells you the direction of the rotation. And also the angular speed. Because 2t, 3t, 4t, they all give you the same trajectory. But the bigger the b, the higher the frequency, the faster the whole thing rotates. Okay. What about this part? This part has nothing to do with rotation. It just makes the rotation as your vector rotates, make it longer or make it longer or shorter. So this one tells you the magnitude. Okay. Therefore, you have three ways. The first one is it shrinks as you rotate, it stretch as you rotate, or it stay the same as you rotate. Okay, so this one tells you the rotation. This one tells you what? This one tells you the shrinking or stretching. Now we can see this. If we type the two solutions into this question, what we got is the first vector, and we have a rotation, which is going to be Oh, no, 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 no. I start from this very point. Okay, this is one of the two solutions I have. Okay, and then you can see you rotate. Meanwhile, you actually keep shrinking because you have a negative 2t there. So you rotate, you shrink as you rotate. That's what you get from the first solution. Now, what about the second solution? It's going to give you another circle, and then you rotate and you shrink. Oh, forgot the vector. Okay, so you have two solutions. Remember, we have the real part, which is the blue, and the imaginary part, which is the green. We let both solutions just keep changing. You can see they both shrink to the origin. All right. So finally, what about the general solution? Well, a general solution will be a linear combination of these two, where our k and s can be anything. So we simply take the sum of these two after we multiply them with a constant. Number one, the trajectory is going to be a linear combination of both. Okay. What I use is actually I use the 2 times the blue plus 3 times the green. So this is the resultant vector. Now, what we will do is we will see as green and blue rotates spiral in. Okay. What will the final linear combination of them do? And you can easily imagine. It also shrinks in because both are shrinking in. Therefore, this one will also shrink in. All right. What if we take another solution? We don't take 2 and 3. We take 4 and 5, or maybe, I don't know, 1 and 2. Because our constant can be anything, right? Our C1 and C2. We just take I don't know, 1, and maybe 1.2. Then we simply just have another spiral. Okay, or we can take 1 s equals 3, and your k becomes 5. Okay. From here, you can see no matter what, the linear combination of the 2 green and blue basic solutions is going to be a spiral. And as they shrink, no matter what, the one on the spiral will also shrink because both parts shrinks. Of course, the one in total will also shrink. All right. So that's the phase portrait we are going to get for complex eigenvalues. So, phase portrait. For complex solutions, it comes from A plus BI t, which equals EAT cosine BT plus I sine BT. The part in here will always have a magnitude 1, so this one only takes care of the rotation, and we don't care too much about the rotation when we talk about equilibriums. Okay. However, this part is the major part, so we are going to write it down. When A is less than 0, e to the negative 2t. When t goes up, this one goes down, the whole thing shrink. When A equals 0, this one stays the same, so you have a circle. When A is bigger than 0, this one stretch. And you can easily draw what's going to happen. If you rotate and shrink, you are going to have a spiral, and you are going to have a spiral sink. Because eventually everything just gets closer and closer to 0, 0. Okay. And similarly, if you stretch as you shrink, as you rotate, you are going to have a source. And you can see the whole thing is leaving and getting bigger and bigger and far, far away from 0, 0. So this is going to be a spiral source. What about the one in the middle? The one in the middle is going to be a circle. You just keep rotating. You never shrink. You never go inside. You never go outside. You stay on the trajectory. So that's how we tell. We do the eigenvalues the eigenvalue is going to have a real and imaginary part. Then for the real part, you just check if it's bigger than 0, spiral source. If it's less than 0, spiral sink, which is what we have for our examples when we have -2 plus minus 3i. Okay, and if we have exactly 0, we have a circle. What about 3 do? 3 only tells you how fast you rotate, like this or slowly like this. Because that's the part only has something to do with cosine and sine. The imaginary part, when you rotate, does not change the size of the vector. Only the real part does. All right. That's everything we need to know about complex systems. We will just briefly mention at the last some examples as before. Do you recall something like this? When we get the harmonic oscillator, which is undamped. Okay, and then we can take an easy case really quickly. Y prime prime equals -y. Just take k equals m equals 1. Okay, then we have the system that is y prime equals v, v prime equals -y. So your A is going to be 0, 1, -1, 0. Determinant. Lambda I minus A. Lambda -1 plus 1. This implies lambda square plus 1 equals 0. So you have lambda is complex. So what's your final solution? Your final solution will be cosine 1t, right? Because technically you have e to the it. Cosine 1t plus I sine t. And moreover, you have times e to the 0 t. So you do have the real part. The real part is 0. So according to our table, you rotate and you do not change, you do not shrink, you do not stretch. Therefore, what's the trajectory? It's going to be a circle, which we have verified for multiple times using a direction field. It is a circle. But now we can say for sure. Okay, so that's why you don't come in, you don't come out, you never go to the equilibriums. As long as you start moving, you move forever. But you do not make your magnitude stretch either. So you keep the energy to be the same. Okay, and you can imagine, you can verify by yourself. I'm just going to skip it. If you start to have things like this, you are going to have damped harmonic oscillator. That's the moment you definitely is going to have something which is spiraling in. Go ahead, try some examples and try to see, wow, this actually happened. And then ask yourself, then in which case will I have something that is spiraling out? Okay, which is actually spiraling, away. All right, so let's close this with some examples. Really quickly. Okay. First system, -2 plus minus 3i. We know because -2 is less than 0. That's the real part. We are going to have a spiral sink. Proved by the direction field. Spiral source, we have something like this. 1 plus minus square root of 5i. 1 positive. You have e to the t times a cosine sine. Spiral source, which you spiral away. Yeah, it's probably hard to see, but you can see, the whole thing as you rotate clockwise, the whole thing moves away. Okay. Oh, sorry. That's the second one. Yeah. Now it's more like it. Okay, you spiral, but you move away from the origin because the real part of your e to the at is going to be increasing because your real part is positive. Okay. Finally, we have the center. That is when we have something with no real part, which means the real part is 0. Then this one is going to bounce back and forth. without losing energy, without more energy. Okay, so that's where we have a center. Oh yeah, I need to be careful here. I said a circle, but the terminology for this one is going to be center, not circle. The shape is a circle, okay, but this is called a center. All right, that's everything for complex eigenvalues. The first one you need to know is how to solve the differential equation, and of course the initial value problem if you have to solve C1 for C1 and C2. The second thing is you need to know how to do the equilibriums. We are going to have 3 different cases, and the way to tell which is which depends on the real part of the eigenvalues. Another important takeaway is for anything including complex eigenvalues, you always have things in pairs, and usually you only have to do one of them because the other one will be almost symmetric, no matter what you are studying. All right, that will be all for this section.